now. Does anybody feel inertial forces? Okay, I claim that you do. Every one of you. I think it depends what you're drinking. Everybody feels some force pushing up against here or their feet, or both. Correct? Everybody in this room? What is that? Normal force. Where's it coming? The floor, the chair. Why? Because we're in a rocket, accelerated upwards, and so you feel inertial forces. Without looking outside the room, you can't prove to me that it's not so. Locally, in this closed environment, in fact, it turns out no physics experiment could be performed in a small enough region, and we'll get to that later, that would be able to distinguish between those two situations, our being on the planet Earth sitting like this, or in a rocket accelerating upwards with the right acceleration such that it gives the same inertial force as gravity. Okay, and that's a consequence of the equivalence principle. And that tells us that we are not in a good inertial frame. We are not in an inertial frame. We are accelerating. So we cannot say that we see something falling, it has a curved world line, because we have curved world lines. We're not capable of judging what has an inertial world line. So from that perspective, we draw a straight t-axis and an x-axis, and we draw these accelerated particles as though they have curved world lines, where they don't. They actually have a straight world line. But a straight world line as seen from the correct context of this warped time. I'm going to bend the time axis. I'm going to curve it around. Okay? In fact, you can imagine that if I made this curvature a specific amount, then what will happen to the world line which has exactly that curvature? It'll become straight. Okay, now again, I can represent it. This is just all kind of very heuristic, so it doesn't really matter, but I could say that the line that's curved this way, right, when I pull this like this, it pulls the top more, so it's this one that uncurves. You see what I mean? And bends that way. It doesn't really matter. Again, I don't want to get into the specifics, but the idea is that
Isn't that curved timeline just straight though?
what kind of reference? What kind of frame of reference?
I guess it would have to be non-inertial, right?
Right, it would have to be accelerated. This unusual effect, this unique effect, that in gravity, although particles are accelerated, they feel in an identical way to a particle that's inertial. So it has both, it works. This fits. Particles accelerated in this region of curved space-time do indeed feel inertial, and stick an inertial particle over there, it starts accelerating. Okay. And we have this picture now. We have a world line curvature field. What would it look like in this eventual theory that we're going to construct? We're going to have a space-time curvature field at every region, at every point outside the mass. There'll be an amount of space-time curvature that's generated by this mass, and a measure of the straightest lines of the timelines, right? Although they're kind of like straight lines, this axis is like a straight line, really. It's kind of inertial, but it's not. It has some kind of curvature. So this space-time, straightest lines of the space-time, the inertial lines, so to speak, the world lines, will have some kind of curvature. And that curvature in that complicated differential geometry theory of space-time curvature will have the same amount of curvature we would expect as the world line curvature, which is the acceleration. In other words, if the acceleration is gm over r squared, which means that the world line curvature is gm over r squared, we have a right to expect that in those situations where Newtonian gravity is correct, which we call the Newtonian regime, so for small masses like the Earth and for slow speeds like we're used to for non-relativistic things where Newtonian gravity gives exactly correct estimates, you can predict the eclipse, centuries in advance and so on. So we would expect that for those cases, this other theory, which is much more complicated and has many more things, will reduce to something which gives the same number. If it doesn't give the same number, it's wrong. Right? It has to give the same number. If it gives the same number, we'll assume that it has the same functional form. When you have two things that give the same number over a certain range for things, projectiles and so on, they're going to have the same functional form. So we have every right to expect that that measure of the curvature of these lines of the straightest lines in this curved spacetime will look the same. In other words, it'll be like GM over R squared. It'll look the same as the curved lines. So what you have really is two perspectives. You have a curved spacetime, and then you have the perspective of people who don't realize that you have this curved spacetime, or call it time warping within the context of spacetime. And they're drawing a time axis straight like this, a space axis like this, because they don't realize that time is warped. When they do that, they're going to see inertial particles and think that they're accelerated, which is exactly what we spoke about before. You're taking